What is the biggest number you can think of? Oh yeah, that's right. I'm supposed to state some big numbers as I cannot hear whatever you'd be thinking. And I also have to go along with the script as well. But first, I need to tell that this video isn't going to be about infinity. Instead, I'm only going to scratch the surface on the scale of some big numbers which are real. Anyway, coming back to numbers, how about the number that you see most of the time on YouTube? 1,000,000. How big is 1,000,000? I know what you're thinking. That's a child's play. Everyone knows it's 7 digits. 11 days. 1,000,000 seconds are 11 days. Not impressed yet? How about 1,000,000,000 seconds? How many days are 1,000,000,000 seconds? Well, 1,000,000,000 seconds are about 32 years. Hopefully, this would have given you some perspective on how big of a difference is made by adding even a single digit to a number. Now let's use it. There are 10 raised to the power 80 atoms in the universe. For reference, a googol is 10 raised to the power 100. And how big is a googol? Well, the heat death of the universe would take place after 10 raised to the power 106 years from now. Yes, even the universe will die once the entropy of the universe has become maximum. This means that if you start counting right now with the speed of 10 atoms per second, it would take you around 10 raised to the power of 71 years to count up to all the atoms in the universe. This is great, huh? You could keep adding numbers to the power of 10 to keep on generating bigger and bigger numbers. But this isn't the only way. We have better and more interesting ways to generate big numbers. Let's see them. This is a googol, whereas this is the factorial of 999, the biggest factorial you can count in Python using recursion, without messing up with the limit, of course. A googol is 100 digits long, whereas the factorial of 999 is 2565 digits long. But what if we use the fastest supercomputer in the world named Summit, made by IBM and Nvidia, which has computing power of 200 petaflops, and count till the heat death of the universe? Well, even then we would have only counted up to 128 digits from the incomprehensible factorial of 999. Even if the whole world unites and create a super duper supercomputer with computing power of 1 quintillion flops, we would still reach 130 digits till the heat death of the universe. So yeah, the factorial of 999 is pretty big enough to blow your mind if you can comprehend it. Anyway, now we know that the factorials can generate really big numbers, bigger than exponential values, or can they? I present you a googolplex. What is a googolplex? It is 10 raised to the power of a googol. No, this does not mean a 100 digits number. This means a googol digits number. So yes, exponential values can be really big, bigger than the factorials. All I's dotted and T's crossed. Wait. What are we even doing? Exponentials versus factorials? Why are we making them fight against each other? They aren't mutually exclusive. They're just numbers. And because they are numbers, we can do whatever we want with them. This is the factorial of a googolplex. It is 10 raised to the power this number. for comparison, a googolplex is only 10 raised to the power 100. I don't think there's any other way to comprehend this number. Anyway, so next time if someone asks what is the biggest number you can think of, just tell them a googolplex bank, and hopefully you would win the game. Except if the number they have in mind is not the number that can explode your mind, but rather implode it. Welcome to the Graham's number. A number so big that if you could think about its scale, your brain would literally implode on itself and create a black hole. This is not an exaggeration to emphasize on its scale. Your brain would actually create so much information that it would have so much entropy concentrated in a very small space as your brain that would exceed the density required to form a black hole of the size of your brain. Luckily though, we cannot think about its scale, not directly. However, we can express it in a different way. This is 3 arrow 3, and it is equal to 3 multiplied by itself 3 times, which can be written as 3 raised to the power of 3. This is 3 to the arrow 3, which can also be written as 3 arrow 3 arrow 3, and that means 3 raised to the power of 3 raised to the power of 3, which equals to 3 raised to the power of 27, and that equals to 7.6 trillion. What about 3 to the arrow 3, which can also be written as 3 double arrow 3, and that is 3 to the power 3 to the power 3 to the power 3 to the power, and this deterioration of 3's, this stacked tower of 3's, equals to these many layers of 3's. You cannot write this number down in ordinary notation. But this is not the Graham's number. For that, we have to go even further. Now we have 4 arrows. And just remember how big of a difference there was between 3 to 2 arrows 3 and 3 to 3 arrows 3, that this number is ridiculously big. It's so big that if one digit of this number occupied one Planck volume in the universe, we still would not be able to express it in ordinary notation. We call this number G1. Now let's see G2, which equals to 3 to the arrow to the arrow to the arrow to the arrow, and it goes on and on and on until the number of arrows become equal to G1. G1 was ridiculously big just because of 4 arrows, and now G2 has ridiculously big number of arrows. And that is so unfathomable that you could never ever even begin to imagine it. Even then, this is still not the Graham's number. We still have to go on. And so we have G3. And as you would have guessed it, G3 has G2 number of arrows. And then you keep going until we reach G64. And finally, we have the Graham's number. I mean, it is truly unfathomable, and I think any kind of verbal explanation of it would be an understatement. But still, the Wikipedia definition of Graham's number is really interesting. It says, it is so large that the observable universe is far too small to contain an ordinary digital representation of Graham's number, assuming that each digit occupies one Planck volume. But even the number of digits in this digital representation of Graham's number would itself be a number so large that its digital representation cannot be represented in the observable universe, nor even can the number of digits of that number, and so forth, for a number of times far exceeding the total number of Planck volumes in the observable universe. Well, that's Graham's number for you, the final boss of this video. As Donald Knuth's paper Copying with finiteness' previous title puts it. Until next time, thanks for watching. Bye.